So section 5.3 is volumes of cylindrical shells. And what that means is we're still doing volume of a solid, but in this case, instead of a disc or a washer, a better idea is to use something called a shell. And the idea here is it's still adding up of an infinite number of, in this case, shells, but it gives us this volume here. So the key thing to see with this is that you see the 2 pi x here, times f of x times dx. And when I show you the picture, you'll hopefully get a better idea of those different pieces and what they represent. So in the first picture that we have here, we have this continuous function, and you can see that it's y equals f of x, and it's just what I just outlined there. It's just this. And then the difference between that and the y-axis, x-axis, is still the idea of the height of that function at any time. But now in a case like this, notice what's happening in this picture is that that function is being rotated around the y-axis. And what's being created is this idea of a cylindrical shell. So that is a cylinder, and of course it has some sort of depth to it, which is your dx or your dy, depending on what your orientation is. So notice we have a slice of it, which is what you see here. So there's one cylindrical shell, and the key thing to see is if we open that up, we have a rectangle, and that's really the key thing to see. So in class I have a oatmeal container, but that is in my office. So right now I have a coffee can that I have taken apart completely. So what happens is you're doing a bunch of these shells, and some of them are, have a smaller radius and some of them have a larger radius. But the idea is if you were to open this up, and I am learning about my strength here, if you were to open this up, and of course this is not what it's meant to do, you're going to see a rectangle, and it has some sort of depth to it, but all it is a rectangle. So you're basically just adding up an infinite number of these rectangles in order to find the volume. So for this one, notice this says that the length of your rectangle is just the circumference of the shell. So it's just the circumference here. That is what that length is. Well, that, and it depends, is either 2 pi x or 2 pi y, because you want to remember the circumference of any circle is 2 pi r. And so that's why you have the 2 pi x within the integral. And then the height of it, as we see, like for example on the one over here, the height is just f of x. That's just how high. And again, the cylindrical shells may get bigger or smaller, just depending, but you're adding an infinite number. So we have that. And this thickness here is just either dx or change in x, however you want to think about it. But once it goes into the integral, it's dx. And that is the volume, because the area is 2 pi x times f of x. You can see that's going to give you all this. And then by multiplying by dx, you're going to get some sort of depth to it. And then that's what creates the volume, those three things multiplied together. So no more of writing in these, but this is the idea. Basically, you have your first slab, which is one cylindrical shell, and then another one, and then another one. And then if you do an infinite number of them and take that limit, as the depths get skinnier and skinnier, you're going to have this. So again, this is the length of the shell, this is the height of the shell, and then this is the depth of the shell. And then that's what's going to create the volume when you integrate from A to B. So let's take a look at an example here. And we've got a nice picture to help us out. So this here is sine of x squared. And it's only from 0 to the square root of pi, so you can see that. And of course that helps us, right? Because then we can see that at square root of pi, we do get 0, because that's just sine of pi. So that's why it goes from here to here. And that this value here is going to get revolved. This whole thing is going to get revolved around the y-axis, and that's what's created here. So basically you want to imagine that that piece has a bunch of smaller cylindrical shells happening down here, smaller cylindrical shells that are getting rotated around, and like that. And then as it gets taller, you're going to get larger cylindrical shells, and then it gets kind of smaller again, and then you're going to get smaller cylindrical shells. So you just want to think about what is, in terms of x or y, depending on the orientation, what is the length and the height of that, and then your dx or dy, and then what are you integrating over. Okay, so this is what we're going to find. So let's think about if you just had one slab, and now we come back to the idea of doing the three-dimensional picture on a two-dimensional plane here. But if you think about one of these cylindrical shells, and if you were to open it up and lay it out, that's what we're trying to do. Maybe a little more like this. Okay. Here. So you take what we see above and you just lay it out, stretch it out. Understand that down here, this length is going to be 2 pi, and then the radius from here to here. But that, of course, is just wherever you're stopping is some x value. So the radius is just 2 pi x. And you can see that because you're going from 0 out to wherever that x is. And then the height of this cylindrical shell is, you know, some value here, but that's just whatever the function is. And in this case, that is sine of x squared. So that's what that is. So that's our height, sine of x squared. And then the depth of this shell is just that dx, however wide it is, and then as you create more and more shells, it gets skinnier and skinnier, and so dx. And so you can see that the volume of this one slab is 2 pi x times sine x squared times dx. And then we are integrating this from here out to here. So let's do that. So we have 0 to the square root of pi of 2 pi x sine x squared dx. So again, the idea there is you're integrating an infinite number of those shells. And then we just integrate like normal, quote unquote normal. So I'm going to pull out the 2 pi, it's a constant, I don't need it there, so why put it there? And then I have x sine x squared dx, and that all needs to stay. And then now we want to think about how to integrate this, and this is more complicated than some of the other ones we've seen so far. You want to recognize that in this case, you are going to need the substitution method. So think about what you'd want as your u. Do you have something, and then do you have the derivative of that something? Hopefully you see that you have an x squared, and you have the derivative of that x squared, kind of, sorta, because you need to replace x dx, which is going to be with 1/2 du. So now you're going to have 2 pi, and if you want, you could change your limits of integration. We've done that before. So when x equals 0, u is still going to equal 0. When x equals the square root of pi, u would be, x squared. So the square root of pi squared is just pi. So we can change our integral from 0 to pi of now just sine of u du. And then we also have that 1/2, and so I can put that out here, and that's going to be great because, as you can see, that simplifies with the 2. So I just get pi, and then now I will take my antiderivative of sine u, so that's going to be a negative cosine u, and that's going to be integrated from 0 to pi, and so we'll have pi times negative cosine pi minus negative cosine of 0. So that'll give us pi times, so cosine of pi is -1 times a negative is +1. Cosine 0 is 1 as well, so we have a minus, a negative, 1, or +1. So we get 2 pi. Now it wants the volume, so units cubed. I can be a little bit closer, bear with me on that one. And so we have the answer to that. So that's our first example. So I'm going to bring back the coffee can. And so in the first example, we were looking at a shell like this. Now we're going to be looking at a shell like this. So when you think about this rectangle now that then has some depth, you need to think about the fact that its radius is going to be a y value. So that's where the 2 pi y comes in. Is going to be from this height here. And then this length here of it, however you want to think about that, is going to be some sort of f of y. And that'll be, you know, what we need to find, you know, depending on what we're being given, if we have a curve or something like that. So we'll take a look at an example, but let's take a look at a picture. So in this case, kind of like what I just showed you there, you're going to be thinking about, so each one of these shells is going to have some sort of height like this. Okay. All right, so it's going to look like this. So this, like here, what this looks like, okay, is going to be the 2 pi y, where the radius is this distance here. I mean, that's what you're being given just from there to there. That's what you have here. And then it's using this kind of notation here, but this is just typically f of y. Now, it depends on the function. We'll see some different examples, but it's the idea of what the curves are, curves are. And then it's going to have some sort of depth, some sort of dy to it. But putting those together gives us the same thing that we had before, just with the idea of 2 pi y, f of y in this case. Okay. Now, let's take a look at this example. So here we have this curve. So notice it's x equals 4y squared minus y cubed. So you have that. And the y-axis. Find the volume of the solid generated by revolving the bounded region about the x-axis. So the idea here is this is going to get revolved. So I'm going to kind of draw it the best that I can here. So you want to think about the fact that it's just a reflection. So this bottom piece here, this is not a part of it at all. We're only thinking of the part that's shaded. All right, so a smart thing to do here would be to think about what that reflection is going to look like, and therefore what this shape looks like. So I will do some symmetry here because it is reflected over the y-axis. So if I can find a few points, that can kind of help me. And I could use the function as well, but to think about what the points are so I could reflect them, but I can kind of see them. So I'm just going to do a few points here and then just kind of try to do some basic reflection of this with the tablet. It's a bit hard, but you know, looks something like that. All right, and then of course what's happening is that piece is being reflected over. So we're just thinking about what the shells look like. So I'll just show you kind of an example of maybe where one of the shells is. So if we're here, then we're coming out here, and similarly coming here, something like that. They should be the same. And the shell that's being created looks like this. because remember this is being reflected around the y-axis. So you're thinking about your, shell, of course thinner and thinner shells here. So something like that, again, doing the best we can here to draw. So we want to find the idea of, say, the volume of one of those shells, like that thing, and then the integration is what's going to give you all the rest of them. So if you think about this shell, we can draw an example of the shell, kind of a thick slab here, but it's the idea. Oof, oof, oof. Okay, all right. So when you're looking at this, a couple things to think about is the thickness is still the dy. In this case, the idea here is that when that shell, if that shell was to be stretched out, the radius is just this distance here, and that distance is just how high you're going along the y-axis. So that's why this piece is 2 pi y, because if you were to stretch that out and measure that, it's going to be the circumference of that circle, and the radius of that circle is just y. So circumference is 2 pi r, so it's 2 pi y. And then if you think about it, going from here out to here is just where that curve sits. And we know that that x value is equal to 4y squared minus y cubed because it's on that curve. And that's why this distance here is 4y squared minus y cubed. And so putting all that together, we're now able to do our integration. Key thing to see is that we are integrating from here, which is 0, 0, up to 0, 4. And these are y values. So notice this is going to be in terms of y. And I'll give you a tip in the last video of how to think about which method you need to use. But we've got 0 to 4 because we're going from 0 up to 4. It gets rotated, but the actual integration is from 0 to 4. And then we'll have 2 pi y, that's that height, times f of y, which in this case is the curve 4y squared minus y cubed. And then we have dy. We can pull out the 2 pi, 0 to 4. We can multiply through, this is a pretty simple integration here, we can multiply through by y to get 4y cubed minus y to the 4th dy. You're obviously welcome to pause this and see if you can get a final answer here. But now we just need to integrate what we have. We didn't use anything special, so just regular integration here. We've got y to the 4th minus y to the 5th divided by 5, integrated from 0 to 4. So we are on our way. Now we just evaluate. I'm going to put the 2 pi to the side. So 256 minus 1024 over 5. And then luckily, you can plug in 0 and get nothing, so that's helpful. And so now we will just have 2 pi, and we can combine those two. If we combine them, we actually get 256 over 5. And that just ends up being 512 over 5 pi. And that is a volume, so units cubed.